So, let me start by asking if you have questions from last week. I hope you have some questions about last week.
It's not directly related to the lecture stuff, but so we have a target space in string theory.
Yes.
Space on, basically. Is there any explanation for the existence of that from string theory?
In perturbation theory, definitely not. In general, I'm not sure what to answer. What you want to? Are you asking something in general about why space-time exists, or
Is there an explanation for it from string? Like, can we say for sure we live on the donut?
I mean the shape of space-time?
Sure, just any of these questions. Because it seems it seems like we programmed
all of those questions, unfortunately, even within a universe described by string theory, are non-perturbative. So it's really hard to say anything about them. At the level of perturbative string theory, so we described a system where you had these 26 coordinates in which the worksheet can move. You can replace that with almost any conformal field theory with central charge 26. And perturbation theory will make sense. Now, you might want to have something like a time direction or something like that in order to get a unitary Hilbert space or something. I'm not quite sure what are the precise constraints. But if you say they take at least one space at one time and the other 24 directions, I convert into something else, I still get a reasonable perturbative string theory. Depending on the CFT you pick, this string theory might look like I'm moving in a fancy manifold, or might not have an interpretation at all, a geometric interpretation at all. I have to say, even our knowledge of what is the space of two-dimensional conformal field theories is very limited. And all of this is just perturbative. Then there is the question, which of these perturbative string theories actually make sense non-perturbatively? And that's harder. So people try to build configurations which are at least perturbatively stable and stable against some of the non-perturbative effects we know about. But it's a cumbersome and exercise, and it's not clear if the answer actually do make sense. So yes, I have very little I can say and trust about this question. Are there any other questions? About ghosts, about VFT quantization?
When we say that we're studying states which are closed mod exact, so we're looking at cohomology, are we usually just looking at top dimensional forms or any dimension?
No, you can look at any forms. Then in the context of finite dimensional integrals, when you do the integral over your manifold, you need to wedge enough forms to sort of soak up all the directional space-time. Or the target. When you have infinite dimensional, when you have path integrals, you have infinitely many b's and c's. It becomes more subtle to understand what's. So in the finite dimensional case, the degree of the forms you needed to integrate was the difference between the number of c's and the number of b's in your integrals. Because the action is something like bc. So pulling down powers of the action, you can get for free as many b's and c's to soak up the integration variables. But then if there are more c's than b's, you need to put by hand some other operators which have c's. And if you have more b's than c's, you need to put extra b's in the operators. in the infinite dimensional setup, you're sort of trying to ask the question, are all the B's and C's paired up by the action or not? Are there some B's and C's that are not paired up by the action? And are there more B's than C's or more C's than B's? What's the difference in the number of B's and C's? So something which is, so if I have an action, so schematically, I have something like, so if I just expand in modes somehow, if I expand my B's and C's into modes, whatever basis of modes I want, right, my action will look like this. Just the quadratic part, the kinetic term in the action, the quadratic part of the action. There will be some bilinear of B's and C's with some coefficients, right, some numerical coefficients. And then product of the B's and product of the C's. So what does it mean for, so suppose that my matrix has some zero modes. Right? So suppose that some of these elements are zero. Then the corresponding B's or C's don't appear in the action. So so for all the modes for which this matrix is sort of integrable, for which I really pair up things, those are not going to give me any trouble. But I need to know, but sort of the problem is caused by the zero modes of the kinetic term. So if there are any zero modes, I need to sort of count the number of B zero modes and count the number of C zero modes and take the difference. And that will tell me how many B's and C's I need to put in my operators. So if you remember, I introduced this sort of symmetry, which was Gauss number symmetry, under which the charge of a B is -1, and the charge of a C is 1. So when I have a symmetry, like usually you think the correlation function should be neutral. If I want to have a correlation function which is not zero, the product of my operators should be neutral. Otherwise, I just apply the symmetry. The answer should not change, but it does change. When I have an imbalance between the number of B's and C's, though, it means that the measure is not going to be neutral. So my correlation function has two operators which have a net charge to compensate for the charge of the measure. This is just precisely the same statement that's saying the number of B's and C's in my operators must match the difference in the number of B's and C's in the measure. But the point is that this notion of, so when the measure is charged under a symmetry, you say that the symmetry is an anomaly. So the Gauss number, something called the Gauss number anomaly, tells you what's the charge of the measure, and so by extension, what's the charge of the operators you need to insert in the correlation functions to get something which is not zero. And this will matter a lot when we compute string theory amplitudes. We'll come back to this again today and tomorrow. And so this Gauss number anomaly can be computed even when you have infinitely many B's and C's. Okay. Any more questions? Does this answer the question? Probably too much. Right. So if I just have C's and no B's and have a finite dimensional set of C's, like when I integrate forms on the manifold, then I have a Gauss number anomaly, which is just the dimension of the manifold. And so I need to use forms of total degree D. if I put a gauge fixing condition, so I'm really integrating of a manifold dimension d minus 1, then my total form degree should be d minus 1, because number anomaly is d minus 1, because in the measure there are d C's and 1 B, and so on and so forth. When we gauge fix on a surface, right, we have gauge freedoms which are given by diffeomorphisms. After gauge fixing, you might worry that it's possible that there could be some diffeomorphism that still fix your flat metric. On the other hand, sorry, I'm message this properly. Maybe I'll discuss it in the specific case of the BC ghosts tomorrow. Okay, so which information do we need about the string theory ghosts? So we learned that we needed some C ghosts which behave like diffeomorphisms, so like vector fields, they have an upper index. And there are some B ghosts that can be conveniently represented as symmetric tensors, traceless symmetric tensors with lower indices. So this is the same quantum numbers as the stress tensor, right? So in particular here I have a BSS, which I just call B, and BS bar S bar, which I'll call B bar. And the fact that they're the same quantum numbers as the stress tensor is pretty much because they are what we use to impose the constraint that the stress tensor vanishes. So the BRST symmetry maps the B's into the stress tensor. In particular, the stress tensor is Q-exact and drops out of correlation functions, which is the quantum version of the classical constraint, the Virasoro constraint. Similarly, I can thus define CS as C and CS bar as C bar. Another reason for which this is a convenient notation is that the action for the ghosts in flat metric is just B del bar C plus conjugate. In particular, the classical equations of motion tell you that C is holomorphic and B is holomorphic. And the opposite is true for C bar and B bar. So really you should think about C of S and B of S. And C bar of S bar and B bar of S bar. And we'll describe this field in more detail in a moment. Other pieces of information that we might need is that classically, at least, the ghost number stress tensor takes the form C del B plus Q del C B, and same for T bar. And also, let me write the ghost number current, which is the current for the ghost number symmetry. It has two components, one holomorphic, one anti-holomorphic, which are separately conserved, a bit like it was happening for the L's, or the A's. And they just look like CB. So when we try to address questions about the imbalance between the number of B's and C's in your measure, you'll really be asking questions about the anomaly of this current. And finally, I should write down the BRST generator. So the BRST symmetry, it's a symmetry, it also has a current, which again has an holomorphic and an anti-holomorphic part, which are separately conserved. And it's a little lengthy expression. There is something like this. This is the stress tensor for the x's. It's just dx dx. Plus bc del c. And same for g bar. So the BRST, in particular the BRST current, the BRST charge, it's just the contour integral. It's just the zero mode of the BRST current plus complex conjugate. Okay. But really, the only BRST transformation we will need is pretty much this, but this is the total stress tensor, which is the sum of the stress tensors for the X fields and the stress tensor for the ghosts. Okay. Mm-hmm.
So as you've written it, both B and C have two free components, is that right? Like
Two
B
components.
and C have two free components each.
That's correct.
So we
That's
won't
correct.
see a ghost.
So we started our life with 3 B's, 2 C's for the diffeomorphisms and 1 C for the wild transformations. But we integrated away everything that looked like Lagrange multiplier. The only things that have interesting actions with derivatives were these components of B and C.
So there wasn't an anomaly, but now there isn't, because the numbers are equal between B and C?
Oh, well, locally, they're equal. So in each patch of your surface, there is no anomaly. But globally, there are some things that don't quite cancel out. So in general, as I said, what matters are the zero modes of the kinetic term. The non-zero modes are paired up. So if you want to do this analysis here, you need to sort of look what are the eigenfunctions for the del bar operator. The zero modes are things killed by del bar. So you can ask yourself, are there vector fields which are globally defined on my surface and holomorphic? Or are there what this calls quadratic differential, something that has two S's? Are there any objects of this type which are globally defined and holomorphic on my surface? And the answer in general is yes. There is a finite dimensional set of them. So there is some finite dimensional space of zero modes for the B, some finite dimensional space for the zero modes of the C. And the difference is the ghost number anomaly. Now, there is some mathematical thing which is a very nice physical interpretation. The mathematical thing is called index theorem. It tells you that when you do things like taking the difference of the dimension of the kernels of del bar and the joint of del bar, this is equal to a quantity which is an integral of a nice density on the whole surface. Something an integral of the, for example, of the Ricci scalar on the surface. You can understand that in very physical ways. In a very physical way, you can take your ghost number current and compute the divergence. So classically, this vanishes. But if you do point splitting regularization and so on and so forth, and you do it carefully, you actually find that there is something here, some number times the Ricci scalar. So whenever you try to do a correlation function and check, so in a sense, you can sort of check the violation of ghost number symmetry globally on the surface by integrating this. You integrate the divergence on your surface, and this is equals to some constant times the integral of the curvature, which is a topological invariant of your surface. So this quantity is precisely what you would get if you count the number of zero modes of these minus the number of zero modes of that. So the fact that the difference between those numbers is this is called an index theorem in mathematics. And this is the quantum field theory proof, that index theorem.
If we take the equations of motion from varying v of that action, we see that the zero mode is the classical solution, right?
Yes, that's correct.
So if we didn't have a classical solution, there would be no anomaly.
That's correct.
Is there a way to understand that?
Well, because it would mean that in this integral, you have everything is paired up. See, the point is that the things that are not zero modes, when you regulate your path integral, like you put some cutoff, so you're just left with some finite set of eigenvalues for del acting on B's or C's. And everything that is not annihilated by del is paired up. So if you're walking away from the kernels, this is invertible. It really gives you a map from non-zero modes of B to non-zero modes of C or vice versa. So you're sure that once you regularize your measure in a nice way, those will not contribute to the gross number. And changing the regulator will only add pair of modes of B and C or some high frequency, or remove them. But it's not going to change the difference between number of B's and number of C's. So in a sense, you're trying to take the difference between two infinite numbers. Right? This is a bit ambiguous. But the kinetic term, or between two different infinite sets, the kinetic term gives you a pairing between elements of these two sets. And you only discuss the elements which are not paired up. Okay, so what is the Hilbert space of the ghosts on the cylinder? Now, take our surface sigma to be the usual cylinder with this complex coordinate S, which is used for discussing the scalar fields. If I just repeat the canonical quantization that for this BC goes to this first order action, you get a very simple answer. It's actually quite similar to what you would get if you were to quantize fermions. This action, if you were to discuss massless fermions on a surface, we would write an action which is really looks the same, except that the indices carried by the fermions are different. So you can expand your B and C in modes. And then you get canonical commutation relations. The B's commute to themselves. The C's commute to themselves. And the B's and the C's are creation operator and destruction operators. I mean, anti-commute to one. Okay. Remember, when we were doing the scalar field, we had an N here. Kind of had to do with the fact that it was a second order action. The reason there is no N is pretty much that there is a first order action. So again, we can say that all the B's with and C's with positive index are destruction operators. All the ones with negative index are creation operators. And we have some zero modes, B0 and C0, and B0 bar and C0 bar. Of course, I also have the B bars. And the bar operators and unbarred operators anti-commute.
Why are we considering a cylinder? Like, isn't the surface on which S lives defined by the motion of the axis?
So ultimately we will want to discuss more interesting surfaces, where it has some strings coming in and going out, right? Analogous to Feynman diagrams. But in order to just know what lives on these semi-infinite cubes, I can start by studying a cylinder. So in a sense, what I'm trying to understand now is which states can we insert in these cylinders as initial and final conditions for my worksheet. So I want to describe this Fock space. I want to combine it with the Fock space to the axis. And I want to ask what are the states which are Q closed modulo Q exact. Perhaps I didn't actually mention it. So when we were discussing correlation functions, I said the operators that we study in the theory are Q closed operators modulo Q exact operators. If I'm studying a quantum field theory in a non-compact space-time, I also need to discuss what's the Hilbert space of the theory, not just what are the operators in the theory. And the statement is the same. You include in your theory operators, states which are annihilated by this Q, modulo states which are in the image of Q. And again, so correlation functions of Q closed operators are sandwiched between states which are Q closed will be well defined and will not change when I shift things by exact amounts, by Q exact amounts. Okay? So when you do Biresti quantization of QED, for example, you will study the space of states of your QED by taking the space of all configurations of the photon and the ghosts, looking at the Q closed states, modulo the Q exact states. And that will give you a Fock space of physical photons, where each photon has only physical polarizations. Here we want to do something similar. So let me define some ground state G, which are annihilated by all the positive modes of B. And B bar. And C. And C bar. By the way, if you're asking yourself why did I pick positive modes, I will just tell you, take this expression, write S in terms of position and Euclidean time. We rotate to Lorentzian time and see that these are positive energy or negative energy modes. Okay. So we want the states to be annihilated by operators, ground states to be annihilated by operators with lower the energy. Now we need to decide what to do with the zero modes. Let me just pick a state which is annihilated by B0 and B0 bar. Now, starting from this state, you can create 3 more states back with C0. So there is G. I can act with C0 and get CG, C0G. I can act with C0 bar and get C0 bar G. And then I act with C0 bar. I go to minus C0, C0 bar G. Or I act with C0 here. So I get four ground states. And because the anticommutator of C0 and B0 is 1, you can easily convince yourself that B0 sends you back. So these 4 states give you a representation of the 0 modes. Now, this state is particularly nice physically because when we do string theory amplitudes, you sort of want to use states which, well, okay, first of all, because it will give us the more most interesting heuristic homology. But anyway, intuitively, if you imagine a surface which has a cylindrical end, right? You ask yourself, what gauge fixing do I actually need to impose? And which diffeomorphisms are part of my gauge group? I probably don't want to include diffeomorphisms that blow up exponentially as I go towards the end of my cylinder. And when I say that when I gauge fixed fluctuations of the metric, I don't need to gauge fixed metric fluctuations which grow exponentially. I mean, I need to impose some boundary conditions to my problem. And a reasonable boundary condition is that my gauge freedom includes diffeomorphisms which don't blow up. And my metrics include metrics which are asymptotically cylinders. And when I do that, see, I need a B for every mode of the metric. Right? So it's natural that I'm to use a state which eliminates all the B modes that grow exponentially. Simply because I don't need to gauge fix the corresponding modes of the metric. And similarly, it's natural to use a state which annihilates all the ghosts, all the C ghosts which grow exponentially, just because I don't need to gauge fix diffeomorphisms that grow exponentially. My gauge group just didn't have them. So when we compute string theory amplitudes, we will put states which typically look like this G tensored with some state in the Hilbert space of the matter, or the X fields.
Can you always guarantee that such a state exists?
Well,
is it clear that you can always choose like a G that satisfies all these conditions?
It's more like a definition. So this definition makes sense.
Okay.
So this gives me a representation. So these and the states obtained from it by acting with negative modes and 0 modes give me a representation of the Gauss modes. This representation is a reasonable quantization of the space of the phase space of the ghosts. You could have tried other quantizations, but I could have asked the same question about the X fields. So, can I say? So, I mean, this risks bringing us into a complicated discussion of how do I decide what's the correct Hilbert space in a quantum field theory? That's a fun question. It's also related to the question of how do I define a quantum field theory? What is a quantum field theory? Right? Now, you can define quantum field theory in terms of just correlation functions on some compact spacetime without ever mentioning Hilbert space. And then the Hilbert space comes in as a derived notion of what happens if I try to cut my spacetime in two. And you can convince yourself that I can write a correlation function as some state created by the past path integral sandwiched with some state created by the future path integral. On the other hand, if you come from quantum mechanics, you're perhaps more used to say, okay, I have a Hilbert space and operators acting on it. And then the Hilbert space is part of the definition of your theory. The operators acting at some moment of time are part of your definition. The Hamiltonian is part of your definition. And then you can use this Hamiltonian to move your operator in space-time, and then perhaps pick a vacuum in your ground state, computing their products in your vacuum. So, right, so I don't know exactly which direction would feel more natural to you. Probably it depends if you come from statistical mechanics or if you come from high-energy physics. Quantum field theory appears in a lot of places. Now, in this context, perhaps you can just take it as a definition for now. I said I'm doing canonical quantization of my ghost system. To do this canonical quantization, I expand it in modes, and then for each individual pair of modes, I build a Hilbert space as the Fock space for those modes. So this Hilbert space I would have found just by quantizing these finite dimensional degrees of freedom in the most natural way. And I do it for all the modes, and I do it for the zero mode, and I'm done. But there are different routes to this question, to this answer. Okay, so I define some gets. I should define the other half of the inner products. So if I want to define a nice inner product on this Hilbert space, it's natural to take a dual state, which I'll call G dual for reason to become clear momentarily, with a property which is sort of annihilated by all the modes that don't annihilate G, and is not annihilated by all the modes that annihilate G. So for this dual state, I would say that G tilde is annihilated by all the Bn's, B bars, C's, and C bars, such that N is smaller than 0. N is annihilated by C0 and by C0 bar. Okay? This is a natural definition of a dual state, which is a nice inner product. Then you can just build your Fock space on top of this, build your Fock space on top of this, and compute inner product in the usual way, just by anti-commuting operators across each other with these relations until they annihilate the state to the left or to the right. On a notational point, we can also define a state G, which is just B0, B0 bar, acting on G tilde. Because such a state now is annihilated by B0 and by B0 bar. On the other hand, C0 and C0 bar act non-trivial on it. So this is sort of more analogous to G. Similarly here, you could have called this G tilde, because it's annihilated by C0 and C0 bar, because C0 squared is 0, right? And B0 squared is 0.
But then, so the inner product of this rod G with cat G is 0?
That's right. So G is 0. On the other hand, G C0, C0 bar G is 1. Okay. I hope I got the correct sign here. Let's see. Obviously, I didn't. Let me see. If I use this sign, B0, I carry it across, pick this guy. No, I pick this guy after passing by. Yeah, I probably needed to put a minus anyway. Doesn't matter. So now, does this make sense? I told you that this is the state which is natural to use when we do string theory calculations. And this is also the state that is natural to use when I do string theory calculations. Now, when I have the cylinder, and I said that the metric is 0, is there any residual gauge symmetry? Sorry, the metric is flat. Is there any residual gauge symmetry? Do you know any diffeomorphisms of the cylinder? We'd map it to itself and leave the metric flat. That would lay the metric flat, but would change the metric, right? Like the length. Is there something even simpler than expanding it? Rotations and translations. That's correct. These are the vector fields del z, del s, and del s bar. Linear combinations of them. So del s, del s bar are residual gauge symmetry. What are the C ghosts? The mode. So these are the constant modes of the diffeomorphisms, which means the constant modes of the ghosts need to be inserted in correlation functions. Right? There are 2 degrees of freedom I have not gauge fixed. So I need to put 2 C's in my correlation function. Exactly the ones corresponding to those gauge freedoms. So this makes sense. At least it's compatible with the idea that I should use this as a state in the past, and this is a state in the future in my worksheets.
Did you just explain that point again?
So I said, so what I'm asking, what mode of the C ghost corresponds to these diffeomorphisms? Just the constant modes. Right. The general diffeomorphisms on the cylinder will be e to the ns del s. For non-zero n, this changed the metric. But when n is 0, they don't change the metric. So this the ghosts that try to fix this gauge freedom, sorry, the ghosts for that gauge freedom, not right, are the C0 and C0 bar. So this is the ghost associated to the translation del S is associated to del S bar. So those are modes of the ghosts which are not paired up with any B's, right? So there is a dc0 bar in my path integral, which need to be soaked by some explicit insertion of C0 and C0 bar. And here they are.
Okay, so are we thinking of G bra G C0 as our out state, and C bar 0 cat G as our in state?
No, I would say this is the in state, this is the out state, or vice versa. Right? And these are extra insertions I need to put.
Oh,
Okay. I mean, you can encounter this sort of statements even when you study a line, a particle, not even a string. Then there is translation of the word line. Anyway, so it was just to say why G is a bit natural. Now, once I have this ground state and this Fock space, I can start computing some simple correlation functions. Among other things, this will help me understand how to define these objects quantum mechanically. So let's do the exercise of computing G tilde, CS, BS prime, G. And let me do it. Let me expand it out in full detail. So there is two sums. I have G tilde, Cn, Bm, G, e to the prime, sorry, e to the ns plus n prime s prime. Correct? So when n is positive or 0, this annihilates. When it's not, I anti-commute, and I get a term that is not 0. So I get something that is like e to the s prime plus e to the minus s plus 2s prime plus dot dot dot, which I can resum to e to the s prime over, oh, sorry, so I want to say that this is the answer. I meant this. Okay. So this is the answer. In particular, it means that this correlation function behaves like 1 over s minus s prime as C and B approach each other. If you like language of OPEs, it means that the OP of B and C is a 1 over s minus s prime. Any questions about this calculation? So this allows to give definitions of a bunch of things. For example, if we want to define the stress tensor by point splitting regularization, you'll do something like this. So it turns out that this is the only divergence you need to remove. Because when you plug this in here, right, you get 1 over s minus s prime squared. And similarly for the Gauss number current, you can just do something like this. Sorry. And similar definitions for T bar and J bar. So here. So one thing you could do using these definitions is to identify the algebra, write down the Virasoro algebra for the modes of the Gauss number stress tensor. So compute essentially how the Gauss number stress tensor transforms under conformal transformations. It's a somewhat tedious exercise, but if you define it turns out that the central charge of the ghosts is minus 26. So the Virasoro algebra for the ghosts has a commutation relations which have an anomalous term proportional to minus 26. Remember that the central charge for each of the X bosons was 1. So because of this definition, because this is actually useful to expand the Gauss number, expand the stress tensor into something like this. So now there are two things that are worth observing. First of all, the total central charge, which is the total conformal anomaly, receives contribution from the number of directions of space-time, minus 26. So you should expect the number of directions of space-time to have to be 26 for this to be 0, in order to have wild symmetry not broken. And you can verify this in the sense that if you compute the square of the BRST charge carefully by taking the BRST current, regulating it, and acting with the BRST transformation on it, and see how it acts on the 0 mode, you find a term that is proportional to d minus 26. So your whole BRST quantization only makes sense if the dimensional space-time is 26. The second observation is that when you sandwich your stress tensor between G and G tilde, the stress tensor for the ghosts, you get plus 1 over 12. Now remember that at some point I told you that the Casimir energy was related to the central charge. The statement was only true for unitary theories. The theory of the ghosts is not unitary, so the Casimir energy and the central charge can be shifted with respect to each other. So here you would expect it perhaps to see 13 over 12, and instead you find 1 over 12. So, which means that now if you take your ground state for the matter fields, and you look at the total stress tensor, if you look at the total Casimir energy from the X's and from the ghosts, I get minus 26 over 12, minus 13 over 12, plus 1 over 12, which is minus 1. This is that minus 1 that we had when we were saying that the physical states are Hilbert at 0 minus 1. The Casimir energy of the matter plus ghosts is minus 1.
Why are you using P and 0 for the...
Sorry, I wanted to have... If I put 0, 0, I really get infinity because it's delta function normalizable. I should put a P here, and then I have a delta, a delta P.
Are we using G and G tilde because they're kind of like the in and out states?
Oh, I could have put... I was just trying to measure... I was just trying to measure this acting on G. For convenience, I can read it out by... I could have just... I could have just put L0 here. I could have just said... I just wanted to read off the 0 mode of T. And so I put a vacuum on the left and a vacuum on the right to kill all the non-zero modes. I didn't need to.
So could you just Sorry, again, how this -1 is related to the -1 of the vacuum energy?
Oh, because we know that on physical states, the total stress tensor has to vanish, right? That's the constraint. So, but I'm telling you, if I act on something of the form 0 times G, I get -1. So I need to raise this energy by 1 with oscillators or by changing the momentum to get a physical state. So the energy I put on top of the vacuum, which is measured by L0, will have to be 1. Now, more specifically, actually use this. Let me look at states of this form. I take a generic mode in the Fock space of the scalars and a ghost ground state. And I ask, when is the rested charge annihilating this state? Well, the rested charge is a bit complicated, but you should remember that it has this very beautiful property that Q anti-commuting with B is L. Because Q anti-commuting with B is a stress tensor, and this is true mode by mode. So that means that if I ask how does Ln act on this guy, I can write it as an commutator between Q and B, acting on this state. Now, if n is positive, right, these annihilate the state by assumption. These annihilate this. So this vanishes. So if a state like this is in the cohomology, it must be true that it's annihilated by this L, by the positive mode of L. But the positive mode of the ghosts annihilate the ground state. So this is the same as saying that Lm of the scalar fields acting on M is 0. Remember, this is one of the conditions where we put by hand to discuss physical states. Here we find it as a consequence of asking for the states to be in cohomology. And similarly, you can find that L0 of x minus 1 must annihilate your matter field here, the state for the x's. So we're recovering the physical states condition. It's relatively straightforward to show that this is also sufficient, not just necessary. So if these conditions hold, then this is true. Well, these conditions plus the L0 bar condition, of course.
Sorry, so how did, what's that first equal sign that's going downwards? The Ln acting on N times G, and then the line below that, how are they related?
I'm saying this equals this.
Yeah. Why?
Just because this is the sum of the L of the x's and the L of the ghosts. So the stress tensor, the total stress tensor is the stress tensor for the x's plus the stress tensor for the ghosts.
And they only act respectively, like.
And they act respectively on each Hilbert space, on each Fock space.
So is it triply true that the L of the ghosts annihilates G?
G was our ground state. So if you try to raise to push the energy lower, there is nothing. If you want, when you expand, if you can explicitly expand your L of the ghosts as a sum of B, M, C, N minus M, So you see that when this is positive, either this is positive, this is positive, one of them kills. It's a bit more laborious, but you can also see that the states that are null in the sense of last week are also Q exact. It's a bit more laborious because if I say that my M takes the form of Ln M tilde for N negative, then I can compute the commutator of Q. I can compute Q acting on Bn L tilde M tensor G. And this gives me a first 10 comes from commuting Q across B. And it's this Ln M tilde tensor G. But I also get other terms when Q acts on M tilde. And one has to work somewhat hard to show that if this guy was actually, that you can keep correcting this expression until you eliminate this. But the outcome is that states which are this form are null. And so the calculations we did by hand last week are actually correct. So the string spectrum we described last week really corresponds to Q closed modulo Q exact states in the Fock space. And so now we know what are the in states and out states that we can use in our scattering amplitudes. The next sort of question that we need to ask is, how do we work with general Riemann surfaces? Right? So from tomorrow on, we'll try to develop the tools that we need to answer to compute an amplitude like this. Where I put here some specific states, and I put here some specific states, and I put here some specific states. So we need to develop the two-dimensional quantum field theory techniques that allow us to study string quantum field theory correlation functions on a funny Riemann surface with generic choices of states on the semi-infinite tubes. Are there any final questions?